I've heard that.
Okay, welcome, have your attention. Welcome to the Astronomy Club of Akron's March meeting. Very happy to introduce our guest speaker, Dr. Patrick Durrell. Dr. Durrell is Professor of Physics and Astronomy at Youngstown State University. He's also the director of the planetarium at Ward Beecher Planetarium. And he's been out several times to talk to us. Last time he was talking to us about his research on globular clusters, and today he's going to talk to us about black holes. Can you have a warm welcome for Dr. Durrell?
Sorry for the technical stuff. I don't know if I got this thing. Testing, test. Oh, look.
Hot dog.
And there was much rejoicing.
The crowd
Right.
went wild.
Well, first of all, good to be back. This is talk number 3, maybe 4, I don't know. So, yeah, previous talks I've talked about some of the research that I'm doing. This isn't research that I do, but you know, I always like to have a black hole talk handy because you can't beat a black hole.
That's right.
I've given talks where, you know, at things where they had multiple things, and the black hole talk always draws everybody. So this is just comes from experience. And the idea here is just to introduce people to the, well, not so much the weird stuff about black holes, but the different kinds of black holes. Certainly when I teach my classes, the way I approach black holes is not, you know, jumping into things like wormholes and things like that. It's, what are black holes? Do they exist? And if so, where? And how do you make them? So that's sort of the way I look at black holes. Matter of fact, I was just teaching my astrophysics class yesterday about supermassive black holes. So some of the stuff that I mentioned here I would have also have said yesterday. But you know, it's always the thing, you know, what is a black hole? Okay, you know, the first question right off the bat, what is a black hole? And there's different ways to try to describe it. But from an astrophysical sense, you know, imagine an object, okay, that is so massive, okay, and there's different kinds of masses, we'll get to that, so tiny and so dense that the speed to get away from it, from the immense gravity, is so much that even a beam of light can't get out, and hence the name black hole. Basically, once you get to a certain distance away from a black hole, the gravity is so strong nothing can get out. You might want to call it a point of no return, the bad news location, or the oops. It all depends on your point of view. I didn't do it. Clean up on aisle 6. So, but you know, when you describe it this way, it sounds very, very strange, and of course it invokes all sorts of things like, okay, bad movies, and all sorts of things. Black holes are popular. Why? Because they're one of the best ways to fill up a plot hole in a science fiction movie. Okay. But what really is it? And really, you know, do they exist? Okay. So, and like I said, the memes just write themselves. What happens in a black hole stays in a black hole, quite literally. But one of the things is where does the idea even come from? Well, actually, the concept of a black hole actually came out of Einstein's theory of general relativity, which goes back to 1915. Einstein himself wasn't very keen on the idea, but I guess the few people at the time who actually could understand what Einstein was going on about, actually predicted that you should be able to make objects that are so massive yet so small that a beam of light couldn't get out. So they actually come out of his theory of general relativity. But I mean, it's one thing to say, well, this could be predicted by theory, But it comes down to something else entirely when you go, do they actually exist? And if so, how would you see it? I mean, describing it as I have, a black hole doesn't emit light. So for those of us, okay, many of you in this room, if it doesn't emit light, how the heck are you going to see it? So that's going to be one of the things. People always ask me for a picture for a black hole, so there you go. There you go. I take requests. It's true. Some of my students at this point start groaning and go, oh boy, he's at it again. The old man's at it again. But, you know, when you say it like that, yeah, there's practically no light. Once something falls into what's called the event horizon, which is sort of like this outer region of the black hole, yeah, nothing can get out. Okay, if you fall in, you're not getting back out. A spacecraft, not happening. A beam of light, doesn't matter what kind of beam of light you have, nothing's getting out. Even if you're close to that location, all sorts of weird things happen. And this is why they're popular in science fiction. Because, you know, close to a black hole, but not inside, lots of weird things can happen. Okay? But again, what's real? Well, going back to, you know, I'm not going to spend too much time on Einstein's theory of general relativity because it is, well, even for those of us who've done degrees in physics, it's GR, as we call it lovingly, is rather complicated. But the basic idea of GR was, and this goes beyond what Newton himself had done, was that gravity is not some sort of mysterious force that binds things together, but it's the bending of space-time. So the 3 dimensions of space, okay, you're all 3-dimensional, whether you like it or not, and add 1 dimension of time. But for, as an example, and people like to model this, and you may have seen these diagrams before. Whenever you see something online or a story about black holes, you almost invariably see things like this. Imagine space-time is this flat sheet, okay? And a massive object, okay, that's the bending of space-time. So if we put an object like the sun or some massive object here, it's like a bending. So light would normally go across this sheet in a nice straight line, okay? If I were to roll a ball across the table, it's going to roll in a straight line, okay? But if you roll the ball and it gets close to this, okay, it's going to change direction a little bit. How much does it change direction depends on how close you are and how strong this curvature is, okay? Now there might be some people who are looking at this going, that's why my golf game isn't so good. But light will deflect, and that's one of the predictions that Einstein made, is light will deflect a certain amount, for example, around the sun. And they measured that, and it turns out he was right. In 1919, they viewed a solar eclipse and noticed that the stars far behind, but behind the sun, were in slightly, and we're talking a very tiny amount, different locations because the light was bending around the sun. Okay? And this is sort of why Einstein became a household name. Okay? So it's the bending of light by massive objects. And it, you know, it could be any massive object, but you know, imagine now something which is even more extreme. I mean, this is the case of the sun or any other massive object. Okay? And this is the thing, I don't have a demo or anything to show, but imagine space-time is the rubber sheet, and the more massive an object is, you get more of a, okay, now bring in the old commercials on people buying mattresses and people jumping on mattresses. You know who you are, okay? But where does a black hole fit into this? Well, what if, okay, a little bit of mass, you get a little bit of curvature in space-time. Okay? If we take something that's the same mass but even smaller, gravity is even stronger. A white dwarf is a good example of that. A white dwarf is a weird type of star that is the mass of the sun, but the size of the Earth. Okay, so near a white dwarf, gravity is much stronger than, for example, gravity here on Earth. Okay, so you can see the curvature is even more extreme. A black hole, and this is where the hole part comes in, is where it, the curvature is very extreme. Okay, matter of fact, okay, if you've ever seen those things at the science centers, those yellow funnels, you put your money in and it goes around and around and it spirals in and goes into the general fund. That's kind of like the idea. This is, if something stays in orbit, if it just keeps going around and around, it's in orbit. Okay? So the Earth would go around the sun here and just keep going around and around. And it keeps the same energy. It doesn't lose energy, so it keeps going around. It doesn't fall in. But in a black hole, there's a point where you can't come back out. And you've probably seen these diagrams before, sometimes in news articles. This is what they mean by space-time diagrams. So if you get too close, you're not getting up. So like I said, this is just the way to describe it from Einstein's theory. But the deflection is important. Okay? And that's why, for example, in science fiction movies, if you get too close to a black hole, light bends in weird ways. Okay? So, for example, if there was a black hole between us and some distant star, okay, you wouldn't normally see the black hole. There's no light coming out of the black hole. How you look for black holes is, what effect does their gravity have on things? And that's the whole, how do you look for a black hole? Black holes have mass. Okay, so the more mass, the more things bend. Well, and that's what people do. They look for this bending. Okay? So where a star is that place, it's really over here, but because the light has had to go into this and come back out, it didn't go all the way in. Okay? It got bent so much, it looks like it's somewhere else. Okay? Technically, although you would never want to get this close to a black hole, technically there's a location outside the black hole where you could stare in front of you and see the back of your own head. Okay? And for some of that's a little more personal than others. And that's why sometimes black holes can be looked at as lenses. This is a still from the animation. Where around the black hole, light gets it's like a lens, but look how it's distorted things. In other words, the light is coming in and just getting bent all over the place and really distorting shapes. Okay? So that would be, but the thing is, well, how would you look for this kind of stuff? Well, nominally, you don't look for just little black holes floating around, because you'd have to be catching a time where you could actually see some distortions. But there are places you can find them, and there's different masses and flavors of black holes. I just put this in for fun. There was a company about 15 years ago, maybe 20 years ago, and I think it was in Europe, and they were selling this carpet. I can't find it online. I would love to have this in our planetarium. It is actually flat. But this would be fun just to watch people. Okay? Have people come in and I could just sit down and watch and have a great time. Okay? This is why I don't get out much. Surprisingly, black holes are some of the easiest things to draw. As complicated as they are. Here's a black hole. Here's the inside of a black hole. Okay, the mass, whatever the mass of the black hole is, has fallen into a point. Okay, and that point, in physics we give it a name. We call it singularity, which is a fancy way of physicists saying, "I don't know." That's really what a singularity is. Imagine a mass that's collapsed in, and there's nothing to stop the collapse. Okay, so it falls into a point. okay? And I mean a point. So imagine for a stellar mass black hole, something 10 times the mass of the sun, and the mass is just collapsed in on itself. And there's nothing to stop the collapse. Okay, that's the other way to approach a black hole is, imagine that the mass is just falling in on itself. Gravity is compressing it, but there's nothing to stop it. There's no force in nature strong enough to stop it above a certain mass. That's the singularity. That's where all the mass is. This event horizon, and then this is the problem. Some movies and TV shows and stuff like to portray a black hole like, you know, like an 8-ball, but the 8's been wiped out. And that's not what a black hole looks like. The event horizon is this. Okay, this is that no man's land I was mentioning. Okay, there's a certain distance around the singularity where you couldn't get out. And that's what this is. Okay. Matter of fact, again, one of the only people in the 1910s who understood what Einstein was getting on about, you know, was the first one to describe this, and it's called the Schwarzschild radius as a result. Okay, like I said, there were probably only a couple of people back then who fully understood everything that was going on. But, you know, so this is like some of the theory behind black holes. Like, according to Einstein's models and general relativity, you can predict what this size is. Okay, there's an equation to it. I'm not going to throw the equation out, but, you know, how big is this? Well, for a black hole of this mass, it's, you know, if it was the sun, that size is maybe a couple of kilometers, okay? A mile or two, not that big. Another way of saying that is if you could compress the sun into something that's smaller than Akron downtown, it would be a black hole. Now, I'm not suggesting you do this, and there's no way to do that, but that's, again, another way to approach what we mean by a black hole. But there's lots of misconceptions about black holes. And the main one is that black holes are considered these giant sucking machines. Okay? And these giant sucking machines. They don't suck. Okay? They are if you're really close to them. And I think this is one of the things. Black holes, there's lots of weird stuff that I'm certainly not going to be getting into. Okay? If you get close to that event horizon, yes, light can bend at wicked angles. Okay? Time and size change to a distant observer. Okay? Things that we call in the business time dilation and length contraction. Yes, there's all sorts of weird things that can happen. But if you're far enough away from a black hole, it acts like anything else with a mass. Okay? Now, how do I know this is there's all sorts of reasons why this comes up as a great misconception. But let's go back to the halcyon days of 2012. Does anybody remember the 2012 Maya calendar doomsday nonsense?
Yeah, the world ended.
The world ended. Yeah, how'd that go? Yeah. Why would I bring that embarrassing situation up? Is because one of the things that was used, people were using as a, you know, one of the doomsdays is that, well, we were going to be lined up with, there's a giant black hole in the center of our galaxy. Give me a few minutes on that. It's like, yeah. But isn't that going to affect us? Nope. It's 26,000 light years away. And it was 26,000 light years away last year, and it's going to be 26,000 light years away next year. If you're far enough away, that black hole has no effect on us whatsoever. Okay? And even if there's lots of free-floating black holes, the Milky Way is so big, it's not like once it's going to suddenly, hey, where'd that come from? You know, sneak up behind you, as black holes do. Okay. But again, how do you find it? Okay. And again, a lot of the game comes on to, it doesn't emit light, but it will have an effect on things that are close to it. And you look for that stuff. Okay? And it's gravity. Okay? Mass and gravity. Some black holes can be very massive, so they can have an effect on light that's around it. It can have an effect on things that are orbiting it. It can have an effect on a star if it's orbiting a star. So we look for that stuff. Okay? And it turns out there are, well, when I originally made this talk, two. Okay, original title is Black Holes, Both Big and Small. But I've amended that a little bit, because we're now finding a third type out there, and I'll touch on that at the end. Okay? So, what do I mean by different kinds of black holes? There are what we call stellar mass black holes. These are the black holes that come from an exploded star. Okay? Those are the little ones. Then there are supermassive black holes, which are the ones that live at the centers of galaxies. And I'll show you how we know. We've known about those for about 30, the supermassive ones for about over 30 years, and the stellar mass black holes for a little over 50. But there's a big difference in mass between those. And it's like, is there anything in between? And it looks like there is stuff in between. So I'll get to talking about those. But stellar mass black holes, okay, this is a prediction that just comes out of stellar evolution. We know enough about how stars evolve that only a tiny fraction of stars can explode as a supernova. Okay? I know some people are waiting for Betelgeuse to go supernova. I wouldn't wait up. But the thing is, we know from stellar evolution that above a certain mass, a star, one way for a star to go is to collapse and explode as a supernova. And that star has to have at least 8 times the mass of the sun. So in other words, this is not happening to the sun. It's not even close. The Crab Nebula, okay? I'm ACA Marathon folks. M1 is probably the most famous example of the remains of a star that went supernova. This is the result of a star that, was a massive star. It blew up, and we saw the light in the year 1054. And this is the aftermath. Okay? Now, not everything that explodes turns into a black hole. Many of them will turn into something called a neutron star, which would see as something called a pulsar. But the most massive stars, the 30, 40 solar mass things, would leave a black hole. Because what's left is too massive to be a neutron star, so it has to, in a sense, turn into a black hole. That's what I mean by the stellar mass black holes. Okay? Massive stars blow up. Much less than 1% of the stars out there can do this. Okay? And certainly the best case of a black hole in the early days was one special object. Okay? Not that this is the time of year to go looking for it, but Cygnus. Okay? This is a nice deep image of Cygnus. Okay? You can see the Northern Cross in there. Some of you, the Veil, North America Nebula, and the Milky Way going through. But in 1970, an object was discovered. Okay? There's Cygnus. But when the first detectors went up into space that could collect X-rays, they found there was an incredible X-ray source coming from the constellation of Cygnus. Now, it took a couple of years before they could nail down where it was of the sky, other than it's in Cygnus. Okay? Sometimes when people ask you stuff and you're looking at the telescope. But it was one of the brightest. If you could see X-rays, this object would be one of the brightest things in the sky. Okay? And hidden. And I had to blow this up. This is not a star you can see with the naked eye. It's actually fairly dim because it's far away. It's a blue supergiant star. It's about 9th magnitude. So technically you could go looking for it, if you know where to look. I've even forgotten the HR number for the star. It doesn't have a cool name, other than it is the location of Cygnus X1. It's the name given to the brightest X-ray source of the constellation of Cygnus. But when they nailed down its position, they said, there it is. It's like, well, it's a blue supergiant star. It's like, you shouldn't get lots of, even a blue supergiant, they don't emit a lot of X-rays. Normal stars don't emit lots of X-rays. So they're like, there's got to be something else. This kind of star doesn't emit a lot of X-rays. And then people measured it and found out it's orbiting something. That is where all the X-rays are coming from. It's orbiting something that's very massive, but you can't see it otherwise. And this became, in the 1970s, the best evidence for a black hole, Cygnus X1. But it's not the blue supergiant. The blue supergiant is orbiting a black hole, or they're orbiting around each other. This is one of many artists' impressions. There are so many online, I had to choose and pick one. But this is basically an artist's impression of what's called, in the lingo, a high mass X-ray binary. This is an example of a blue supergiant, and we can watch the star. We can use the Doppler effect, we can watch it move. It's orbiting something that is 21 times the mass of the sun. Okay, we can do that from physics. We do that with binary stars all the time. Problem is, you can't see the object. Now, if it was 21 times the mass of the sun, that's another blue supergiant. Well, it's not, we know there aren't two blue supergiants there. We would have seen that. So it's orbiting something, and that something is what's emitting a whole bunch of X-rays. And as people started to understand it, this became the best evidence for stellar mass black holes. Okay? We can watch the blue supergiant move because of something we can't see that is far too big to be a white dwarf or a neutron star. Now, I just said nothing can come out of a black hole. Here's the important thing. When I say X-rays are coming, they're not coming from the black hole itself. It's this disk of gas that orbits. Basically, there's this disk of stuff orbiting around the black hole. And for it to stay in orbit and not fall in, okay, no screaming, because in space they can't green screen. It has to be moving really, really fast. This is called an accretion disk. This is where the X-rays come from. Okay? The X-rays do not come from inside the black hole. And we've now seen a number of these. The centers of galaxies do this as well. You get a huge amount of energy when you got gas that's moving so fast that it's jamming and making X-rays. So this is one of the best examples. There aren't that many of these in the galaxy. This is one of the few cases where we know a black hole is orbiting a star. So those we can find. Most black holes won't be in this position, but when you do, we can actually study their properties. Okay? That's a still from a video. My videos aren't working on this computer, but, and again, the blue supergiant, it's close enough to the black hole that it is losing matter, and the matter is spiraling in and basically zooming around the black hole like this. Okay? And for the longest time, this was the best example. Okay, people would say, do black holes exist? Cygnus X1, there's Scorpius X1, there's some other ones. Okay? But there's only a few of those in the galaxy. But those are the special cases. Okay? Now the thing is, most black holes, there should be lots of black holes around, but they're just not in those systems. So you can't see them any other way. Now, a decade ago, a breakthrough was made in something called gravitational waves. Okay, this was a way people have always wanted to go looking for black holes, and they finally succeeded in 2015. And that is, now unfortunately the video is not going to run, but if you have a situation, I mean, you can have a neutron star orbiting a star. You can have a black hole orbiting a star. You can have a black hole and a neutron star orbiting each other. You can have two black holes orbiting each other. And you can get those. Over time, if two black holes, because of general relativity, they will slowly work themselves together. And when they finally spiral in and coalesce, you make a bigger black hole. Yay. Okay? But when they do that, they release these ripples in space-time. That's these little things here. And we now have detectors on Earth that can pick up those signals. So it's not light, but it's ripples in space-time. They're very, very tiny, and you need an extremely precise instrument to do that. And something called LIGO in the United States is one such case. And they finally found the first one of these back then. Basically, it's like you look for radiation from distant source, not even in our galaxy. And these little ripples go through space, and if they intercept the detector, you get a little bit of motion and a chirp, okay, as it spirals like that. And there's the theory and the data. And they finally found the signal. And the signal, there's enough information in the signal to tell you what is the mass of the thing that got made. And they're typically a few tens of times the mass of the sun. Okay? Two regular stars wouldn't coalesce like that and create that signal. You need to have a black hole to do this. So that was our other window into black holes. So how many have we found? This diagram has probably been updated in the last couple of years, but I haven't updated it. This is a famous diagram people are using because it's like, what is the mass of things? This is in mass in solar masses, so times the mass of the sun. If something is low mass, it could be a neutron star, okay? Which, like I said, we see today as pulsars. But above a certain mass, neutron stars can't stay together. The gravity would be so strong as to squish it into a black hole. So we see neutron stars here, then a gap, and then above that, everything is black holes. And these are the masses of black holes coming from gravitational waves. So we see a bunch of them, 5, 10, 20, 40, even up to 160 times the mass of the sun. So they're out there, okay? And they are finding them with new techniques, okay? How many black holes should there be out there? Well, since some stars that explode can become black holes, we can actually predict roughly how many there should be. There should be tens of millions of them in the Milky Way. I don't want anybody to be alarmed. Remember, the Milky Way is a big place. Okay? The Milky Way is filled with over 200 billion stars, and there might be a few tens of millions of black holes. Stars are already spaced far apart. Okay? We have our sun. What's the next nearest star? Proxima Centauri. That's 4 light years away. There's a lot of space between us and it. So the amount of space between us and any black hole would be even further. So don't worry about that number. Is this a problem for us? No. Okay? Space is big. You can take my word on that. Okay. But there's other kinds of black holes. I like this one.
So true.
It's not my dog. I have schnauzers. There's no way you could get him to sit still like that. Okay. But starting in the 1990s, people started discovering a totally different type of black hole. And the two, while they share the name black hole, are not made in the same way. And it goes down to our Milky Way. This is a picture of Milky Way from Australia. The Milky Way, the core of the Milky Way gets higher in the sky, so it looks even more impressive than you can get from here in the United States. And it comes in the form of a radio source that was discovered in the very, very center of the Milky Way. We've known about it for almost a century. Sagittarius, in the middle of the constellation, or off to one side of the constellation of Sagittarius, is a bright radio source that goes by the name of Sagittarius A star. Could we have come up with a better name?
Definitely.
Certainly. There's lots of cases in astronomy where we could have come up with better names of things. Okay, I'm sure you can already think of some. Okay, where astronomers drop the ball, let's face it, on naming things. But at the very center of our galaxy, there's a very strong radio source. There's a big source there called Sagittarius A, which is the brightest radio source in Sagittarius. And then when we got bigger radio telescopes, we saw that there's a little point thing in there. So we call it Sagittarius A star, or just for short, we call it Sag A star. Aren't we clever? Okay. Now this is the black hole I was talking about. The center of the Milky Way is 26,000 light years away. Okay. We're in a giant spiral galaxy, and we're about halfway out to the edge. Okay. So we're not close to it, but this object is at the very, very center of the Milky Way. But how can we tell if there's a black hole? Will we do the same tricks? Okay. This is a radio map, okay, using any number of the large radio telescopes. This is a radio map at the very center of the galaxy. And there's all sorts of neat things, including this little thing called the mini spiral. This is gas. But Sag A star is this little point right there. So again, how would we tell what's at the very center of the galaxy? Well, we try to look at things very close to the center, and we see what they're doing. And to me, this is, you know, there's lots of areas of astronomy and astrophysics that I like that have nothing to do with the research I do. This is one of my favorites. And that is, for decades now, two groups of scientists, one based at UCLA and one in Germany, have been using big telescopes with infrared detectors to study the very middle of the Milky Way. Now we need infrared detectors because between us and the center of the Milky Way is a lot of dust. There is so much dust between us and the very middle of the galaxy. We can't see regular stars. Even the Hubble telescope couldn't see stars in the middle of our galaxy. Okay? Stars in the middle of our galaxy would be 30 magnitudes fainter because of the dust. So we must use infrared. Infrared cuts through the dust, and the dust doesn't block as much light. And what these two groups done is, I still always find astounding, is this is the very middle of the Milky Way in an infrared telescope. This is 1 light year across at the distance of the center. And in here, Sagittarius A star, it's not actually the bright thing, but that's just the location of it. There's nothing at that location in an infrared telescope. Okay, the very middle of the galaxy is a radio source, but in the infrared, there's nothing there. But there's a lot of stuff around it. And these are baked stars. They're called the S stars. I'm still not sure why. I think when they made an early catalog, they just said S1, S2. But here's what's amazing. Like I said, the middle of the galaxy is 26,000 light years away. So it's a bit of a hike. But what they've been doing over the last few decades is monitoring these stars, and they can actually see them move. Okay? the stars that are right around here, over years, you can actually see them moving. You can actually trace their orbits. And they're all orbiting Sagittarius star. Now, like I said, unfortunately the videos aren't working here, but these are the stars. The fake star here is the middle of the galaxy. And these are all stars, okay, that orbit around this thing. Okay, SO2, this is the most famous one. It has an orbit that looks like this. Okay, goes around just like this every 16 years. We've seen it do an orbit and a half, so we've watched it. So these things are orbiting something in the middle of the galaxy that we can't see. It's not emitting any light. Now, the power of physics is that if we know the orbit of something and how big the orbit is, we can figure out how much mass there is. Okay? And both groups have been studying this, and they get the same answer. Okay? Okay? Basically, this is like a caricature of what's going on. They're basically tracing that all these stars are orbiting around something that is very small, but very, very massive. And how small? Well, it depends. What's the closest that something gets to it and still comes around? And they've gotten the observations down where they can resolve something down to the size of our solar system. Something is 4 million times the mass of the sun, but it's smaller than our solar system. So you can't just make well, maybe it's a big cluster of stars. Okay, that's pretty close for a bunch of stars, and we'd see them. That's the kicker. It's like, well, maybe it's a bunch of weird stars. Are they weird that we can't see anything? What's the weird kind of star that we can't see? A black hole. And both groups getting the same mass. From physics, we can figure out the mass, and that a supermassive black hole lives at the center of the Milky Way. And the mass is, the latest numbers, 4.2 million times the mass of the sun. This is not the same kind of black hole like in Cygnus X1. This is a different flavor of black hole. They have to form a completely different way because you don't make stars that massive and blow up. So people are still trying to understand how you make such big black holes. For all the work that both these teams have done, they got the Nobel Prize. The leaders of both teams, Andrea Ghez at UCLA, is one of them. 2020 Nobel Prize in Physics. Okay, the two of them. Gerhard in Germany. Okay, for this. It's very careful work, it's very interesting work, and we know enough physics. Yeah, it's pretty solid. So for the longest time, the best evidence that black holes existed was that one. Okay? I see that it's very convincing. There's no wiggle room anymore. Okay? You can come up with some weird thing going on, but at some point, you can't just do that. Yeah. Does such a black hole have any effect on us? No. And I'll repeat, no. Here's an overhead view of the Milky Way. Okay, there's us, the black hole, parking. So that's where it is. Okay. But what might surprise you is supermassive black hole sounds like a giant monster. It's really not. But still, it's massive, so it must have an effect on things around it. And it does. This is something I actually teach my astrophysics students. How far away from the black hole does its gravity dominate? It's out a few light years. Maybe 10 light years. We're 26,000. We're good. Okay? Now, in that inner 10 parsecs, things are orbiting at high speeds, but they don't fall in. That star I mentioned, SO2, it's a famous one for astronomers. It goes around, it doesn't fall in. It comes to within 120 AUs. AU is the distance between the Earth and the Sun. Comes out, no problem. It's orbiting the black hole just fine. I mean, not that I would want to be there, but, so it's not getting sucked in, and it's less than a light year away. It's very close to the black hole. So, again, even that star is far enough away that it's not getting sucked in. Okay. Then we start looking at other galaxies, not to the same level of detail, and sure enough, the consensus is now 30 years later. Any big galaxy that we've studied with enough precision, they all have them. Supermassive black holes appear to be in the middle of all big galaxies. It's a feature, not a bug. Okay? The most famous one, out of the Milky Way, is M87, the center galaxy of the Virgo cluster, which you guys have seen me talk about before. This is the big Kahuna galaxy in the middle of Virgo. Okay, this is the time of year to go looking for it. Well, maybe more into later in March and more into April, but. And this is the galaxy with the most massive black hole in the local universe. Okay, in the middle there is something with a jet. You can't see it in this picture. Okay, there's a zoom in. There's this jet coming out of the middle. People have seen that for decades. A very high-powered jet of material is coming out of the middle of that galaxy. When they study a disk of gas that's in the middle, it's about 1 billion times the mass of the solar system. The sun, sorry. So this is much bigger than the one in our galaxy. Ours is only 4 million. Okay? Yeah, and yes, by the way, I should add, even today, that 4 million, as far as galaxies go, we have one of the smaller supermassive black holes. It's just a baby compared to some of these. This one's a big one. Okay, this is a giant one. And it's one of the most massive known. And it's in a galaxy that's more massive than our Milky Way galaxy. And sure enough, 9 years ago, radio astronomers used radio telescopes all around the globe and combined them, okay, using a technique called interferometry to mimic a telescope the size of the Earth. They call it the Event Horizon Telescope, because there you can get really high resolution, like far higher resolution than Hubble or James Webb can get. But it's very hard, it's a very difficult observation. You have to collect radio observations from all around the globe. They have to be precisely synced together. Okay, clocks are very important for this part of science. And they imaged the black hole. Not the black hole directly. This is the shadow of the black hole in M87. When this was released in 2017, a lot of us, our jaws dropped. The resolution is not quite enough to show you the event horizon. But that ring, that little donut, is about 3 times the size of the Schwarzschild radius. This actually, so the black hole is not this thing. The event horizon would be about that big. Okay, so you can't see that. What you're seeing is light that's around the black hole getting bent so badly it forms a ring. So that's why they call this, it's actually called the photon ring. This is now the best evidence that black holes exist. And what would cause this ring? Something that is about 6 billion times the mass of the sun. So this is zooming in into the very middle of M87. Now, we're starting to get images like this. All big galaxies we expect at some point they all have big black holes, and early on in their lives they were probably feeding, which is when gas is actually falling in and the black hole is feeding on it. They send out jets of material, and that's the jet in M87. And the photon ring is this area, again, it's not from the black hole itself, it's stuff around it. It's like a disk around it. But the problem is that the light is so warped that it comes to us in this sort of ring shape. It's a really odd thing. And again, the event horizon for this size, we know how big it would be, is much smaller than that. So we can't see the event horizon. But there it is. And again, the evidence just keeps mounting. They also, at the same time, took data of our black hole in the middle of the Milky Way and got a similar image. It looks almost exactly the same because it's about 2,000 times closer than M87, but it's also about 2,000 times less massive. So the two basically cancel out. But there is Sagittarius A star, and there's the photon ring around it. We're finding these things, and they are there. We still don't know how they got there, though. Okay? Like I said, how do you make a black hole that is billions of times more massive than the sun? It's not from an exploded star. Probably early on, big black holes formed, and they started merging together to form them. Okay? But that's still a problem people are working on today, is how fast do you have to merge black holes to make these big ones? Turns out you got to do it pretty quickly. That's what James Webb is finding. So we are finding both the little black holes and the big ones. This is a still from a video where someone actually modeled, using general relativity, you can do this on a computer, spinning light in a disk around the black hole and see how it gets all warped from gravity. Like I said, we're really close to the black hole here, so things get really crazy. Okay? You don't want to fall in. You don't want any of that. Okay? And they all have them. Like I said, Andromeda, it has one. Any big galaxy that's close enough that we could get enough of the look has them. We only have those images for the two galaxies. But they are a normal part of galaxies. So when we talk about how do you make a galaxy, you have to include how did it get its black hole in the middle. It's a feature. And again, you can't make them the same way. Okay? Probably some of them got bigger because two galaxies collided. They each have a supermassive black hole inside. And when those two galaxies merge, the two black holes merge. And they make one nice, bigger, happy, supermassive black hole. I have no idea how to tell how happy a black hole is. Very quickly, though, I do want to add that we're still changing on this because people are saying, well, if black holes merge to make really big ones, there should be medium-sized black holes out there. The problem is they don't make as strong a signal. They're much harder to find than the other two. And for decades, people have had false starts. Oh, we think there's an intermediate mass black hole in the middle of this thing. Then people look at the data again and go, no, I'm not buying it. There were a lot of claims over a decade or two, but they should be there. Medium sized black holes. And I bring this up only because a year and a half ago, I think they may have finally have the smoking gun. So we're not talking the big galaxies. What about little things? Like a globular cluster. Has anybody here ever had the chance to see Omega Centauri? Okay, the big one. You can't get a really good look from here, but yeah. Omega Centauri is very low in the sky from here, named after a star, but it's actually the biggest globular cluster in the Milky Way. We call it Omega Cen, and it is big. Probably 1 million stars in this one. So it's the most massive globular in the Milky Way. So what a team of scientists did is using Hubble data that goes back 20 years, is they looked in the middle of this thing to see if there's stars moving quickly in the middle. And the answer is, yep. Now again, I gotta see what picture comes up. Okay? They look deep in the middle. You can only do this with Hubble. Okay, if you've ever looked at a globular cluster, you know it's a bit of a mess in the middle. So you need Hubble to see this. And here's the stars in the very middle, and here's the middle, the very middle, the dynamical center of the globular cluster. And by weighting data over 2 decades, I put the arrows in. There are stars in the middle that are moving very, very fast. We know how far the star cluster is. We know how fast those stars are moving. If there wasn't a black hole in there, they'd have left by now. They're moving so fast. Why are they still there? So, best evidence that yes, there's an intermediate black hole in here, about 20,000 times the mass of the sun. So, that is new, and we're still learning more. This is just the beginning of trying to understand all the different kinds of black holes. And I will just simply end by saying, you don't want to visit one. I strongly suggest against it. You've probably heard of spaghettification, it's made popular by Neil deGrasse Tyson. That's because the thing is so massive, people say, well, are there wormholes inside? I said, you're not going inside. You're not going inside. The tidal forces, if you were falling in feet first, the gravity on your feet, I'm assuming you're falling in feet first, is stronger than the gravity pulling on your head, even though it's only like about 6 feet. Okay? These are called tidal forces in the lingo. The closer you get, the stronger. Your feet get pulled more than your head. That's not good. You would get stretched out like an intergalactic version of the rack, and you would be nothing but a string of atoms working its way towards the black hole. So don't bother visiting. Thank you very much. I always want to add some travel tips at the end.
We're open for questions.
So I mean, that's true on Earth too. The gravity at your feet is higher.
It
than
is,
your head because the Earth is nowhere near as
But
massive.
because the difference in gravity is so little, it has no effect
Well,
on
the
you.
atomic force in your body is keeping
Yeah,
you together.
it's not even close. Matter of fact, it's just an extreme version of what gives us the tides. This is what gives us the tides on the Earth. The fact that the moon causes the tides on the Earth, and that's because the gravitational pull between the Earth and the moon, there's a little bit of a tug more on the front side of the Earth than the other side of the Earth. It's not much, but it makes enough of a difference that water flows to the close side and the far side. And that's why we have 2 high tides, 2 low tides every day. So, and this is just tidal forces to the extreme, where it grips ya, part laddie.
With light being a very small part of the electromagnetic spectrum, does the breadth of the electromagnetic spectrum act the same inside the event horizon or outside, or?
Well, they're all, first of all, Because they all types of light move at the same speed, okay, the speed of light. If you go inside the event horizon, they're all treated equally. None of them can leave. So it doesn't matter if you're an X-ray, or an optical photon, or if you're a radio wave. They all travel the same speed, so they all cannot escape the black hole. So in that case, it doesn't matter. Nothing, like I said, once you're inside the event horizon, nothing's getting out. The only stuff we see, like accretion disks and stuff, is all stuff outside of the event horizon.
It's really a question about the physics, thinking through this. As if a rock gets inside the event horizon, I think this phenomenon will happen to get torn apart. But is there,
Eventually, yes.
Is there some kind of a terminal velocity of how fast something gets going before it goes in? And if it's going that fast, that means it should be becoming more massive and smaller. And how does that work?
Well, it's not physically. It appears from an observer far away
Right.
that the mass is changing.
Yeah.
You wouldn't feel a thing. If you were falling through the event horizon, you wouldn't notice anything different.
But I'm thinking of, from the point of view of the black hole,
You're in the same reference frame as the black hole if you're falling in.
yeah, I'm talking about some piece of material from space falling in. I'm just thinking of that, does that mean that ends up with more mass effectively hitting the
Yes.
gas hole?
Yes, and black holes can get more massive by pulling stuff in.
Yeah.
Yeah, yes. Well, the mass will definitely increase. Yeah, because now that because basically your eventual fate, or the fate of the rock, will be to work its way into the very middle and join all the rest of the mass at the singularity.
But that addition is really what the mass was before it started.
Mhm.
It just would appear.
Yeah, it's not magnifying the mass or anything. Okay, you throw a bowling ball in, and you're going to increase the mass of the black hole by a bowling ball. So it's not going to change in that sense.
Do black holes ever dissipate?
Technically, they can. But technically doesn't mean they have. Okay, the whole idea, and I'm not an expert on general relativity, I will add. The idea of this thing called Hawking radiation, the idea that, at the very edge of a black hole's event horizon, basically matter and antimatter can, you can have, light photons can, high energy photons can create two particles, and two particles, matter and antimatter, can get together to make light. It goes both ways. And technically, the idea of Hawking radiation is that if, at the event horizon, if this happens, one particle might actually get a chance to leave and the other one stay, which would mean a very slow leakage. It would take a very long time for that to happen. Maybe little ones, but none of the things that we're talking about, several times to millions of the mass of the sun, would dissipate in any kind of time scale. So, yes, technically, yes. In any kind of time frame that we know, no.
I seem to, excuse me, I think I remember hearing about other globular clusters, like maybe M15. Is there anything believable about a black hole in those?
The data are nowhere near as good as the one I talked about for Omegaset. M15 is one of the ones where people have claimed, based on what's called the velocity dispersion of the stars. The problem is an intermediate black hole only bumps up the middle speeds a little bit, so the signal is very hard. You can say, I think it speeds up in the middle, but the error bars are large. So right, as far as I know, none of the other globular clusters are as well done as Omegaset, because they use other techniques to get masses of the very middle, but they're not as high resolution. The Omegaset result is kind of like the Milky Way stars. We're actually having the speeds of individual stars and arguments that are, if these stars are going this fast, if there wasn't something more massive in the middle, they wouldn't be there. They would have left the globular cluster long ago. So no, it's not the same level of detail. I imagine there are people who are going to try it. I don't know if they are, but I hope so. But no, I think, that's why I think this Omega Centauri result that I mentioned is kind of like, okay, at least to me, who's not a black hole person, is a lot stronger to me as far as a thing. So yeah, does that mean, I mean, if it's in one, should it be in more? Probably. It's just showing it is hard. And that Omega Centauri result is amazing in the amount of patience and careful analysis to do that. I mean, that is hard stuff. So I'd like to think that there were black holes inside lots of globulars.
So much other scientific advances that improve resolutions.
What you've got to improve the resolution.
Yeah.
That's
I mean, somebody
really
may
what
be
it
able to
takes.
do it in their backyard in 100 years.
Yeah, well, and that'll be quite interesting 100 years when,
Right.
you know, someone says, you know, Mom, look at this. Oh, there's a black hole inside that star. That's fantastic. Put it on the fridge. Yeah. So, waiting for those dates.
Is there a record-setting supermassive black hole that,
There have been a few, I don't remember which one. There are a few that are close to 10 billion. There's a few that are more massive than M87. I just can't remember which galaxy. Because the error bars are also pretty big on those. Because again, they're not quite as, their mass is, the quality of the data is not as good as what we have for M87. So yes, there are a few galaxies, and there are a few galaxies more massive than M87. One of the things that is remarkable about the big galaxies is that there's actually a rough relationship. Bigger, more massive galaxies have more massive black holes. Okay, it's not perfect one-to-one. I think the number is, the typical supermassive black hole is about, I want to say 0.3% the mass of the entire galaxy. It's actually called the M sigma relation, and people are still trying to understand how we get that. But if you plot the data, it's actually, it does look like a straight line, but there's still quite a bit of scatter. But yes, so typically, many galaxies follow that. So Milky Way is not as massive a galaxy, so it is a less massive black hole. M87 is a very massive galaxy, and it correspondingly has a bigger black hole. So somehow the mass of the black hole knows about the mass of the entire galaxy. That relation still stands after 25 years. So that's going hand in hand with trying to understand these things. More questions?
Read about something called a white hole. Is that ever been observed, or is that just somebody's?
I don't know a thing about white holes, and no, has it been observed? No. No. That's the thing. I'm not the guy. I don't do the theoretical side of the like white holes and you know, people jumping to other dimensions and stuff like that. I'm an experimental astronomer, which means show me the data, show me that they exist and that there's star stuff going around. But no, if there was a white hole, someone would have mentioned it. But again, you'd have to be in the black hole to escape via a white hole. And like I said, you're not getting in.
One of your slides on the vertical axis said solar masses, and then, was that within the Milky Way, black holes?
No, actually, a lot of those black holes from the gravitational waves, those are from other galaxies. The thing with gravitational waves is that the signal can go for a very long time. So when we pick up these signals of two black holes merging, they're not local. Some of them are halfway across the observable universe.
Well, because on that also, there were these, some of them, there was like a curved line connected.
Yeah, the curved line is because the idea of when they get these signals from the gravitational waves, they can figure out the masses of the two participants, and when you put them together, that's the curved lines. So in other words, they can tell you, okay, like the very first one, I'm going to paraphrase because I don't remember the exact numbers, but I believe the first one discovered was the signal was what you would expect from a 30 solar mass and a 50 solar mass black hole. So when they combine, you have an 80 solar mass black hole. So those things are both, that's what those curved lines are. It's the individual black holes and then the final product put together. Because that's the thing, to get those gravitational waves, the black holes have merged. So, and they can, like I said, the signal can tell you at least the ratio of the two masses involved to make those signals.
That's another thing I would expect they're working on, is more sensitive LIGO type.
They are,
observatories.
and that's going to take more funding. They've already made improvements to LIGO, and they keep finding them now. But yes, the sensitivity needed to even pick those up in the first place is remarkable. Okay? It's like, do you feel those ripples? You're not going to. It makes shifts of the order of 10 to the minus 24 meters, if I remember. So you're not going to feel it. So if you're just like going to work and suddenly you feel good, that wasn't a gravitational wave. So I'm just saying. That just means the coffee was a little extra strong that day. So, but yeah, no, it's, yes, now that they've done it, it took decades just to get to find the one. Now the floodgates have opened, so now they want to make better detectors. And now, like I said, in some cases, some of those things on there were in, black hole neutron star merger, and even some neutron star mergers, which are important for other reasons.
Yeah, I figure as those get more sensitive, they'll start seeing more of those.
They'll start seeing more of those things, yes. But the easiest things to see are the massive stellar black holes. So your 30s and your 50s getting together to make an 80. Those are easier to pick out than a 4 and a 2 kind of getting together. So.
Any chance of seeing gravity waves from the Big Bang?
No, because there, you're not talking about gravitational waves, because the gravitational waves, as these two black holes in spiral, you still have regular space-time. It's just making these extra ripples, so you wouldn't be getting them from that. At least as far as I know.
There's a thing called Candacelari limit.
Chandrastic curve limit.
Yeah, that it's like 2.3 times the mass of the sun, and when they implode from a red giant.
Oh yeah, the mass limits. Yeah, that's one of the things they're still trying to find out. If the core of a star is less than 1.4 solar masses, that's called the Chandrasekhar limit. That's the limit that a white dwarf cannot cross. If a core has more mass than that, and that's why they say stars above a certain mass will explode, then you can end up with a neutron star. Basically, a white dwarf is, like I said, the mass of the sun, the size of the Earth. But once the mass of that thing gets to be bigger than 1.4 solar masses, the gravity is so strong that what holds the white dwarf up just collapses, and it would just collapse into a neutron star. There's a similar limit for neutron stars, and the problem is, once you break a neutron star, there's nothing to stop it. And that's where you get into the black hole. That number is not as well established. It's not as clean as the Chandrasekhar mass. For white dwarfs, it's 1.42-ish times the mass of the sun. For neutron stars, it's somewhere around 2 to 3. And that's as good as I can give you. And so they're trying to find out, and that's why there's that gap. Neutron stars and black holes. They're like, where is that limit experimentally? And it's kind of tough, that dividing line. So there is a limit. I've forgotten what it's called. The something Volkov limit, I just forget the first name, is the kind of similar one for neutron stars. But certainly above 3.5 times the mass of the sun, neutron stars cannot hold up. And if a collapsing core of a star is bigger than that, it can only fall in to become a black hole. So that's what those limits are about. So that's why when they say there's something big in Cygnus X1, and it's 21 times the mass of the sun. We know it can't be a white dwarf or a neutron star, okay? Because you're very comfortably over those limits. So that's why it's sort of like a process of elimination. And it's like, well, is there anything between a neutron star and a black hole? Not that we're really aware of. Quark stars maybe, but you know, you're starting to get into even more crazy sounding things. So, did that help at all?
Awesome.
Well,
Just had a question about, we observe, objects go into the event horizon, maybe even like, get to singularity or whatever. But like, do astronomers, like, or people that are taking said observations have like, documentation of what celestial bodies like are gone, like, like a graveyard of stars or, like some lists?
oh yeah, those black holes that I showed you, there's definitely a list of them. The ones from the gravitational waves. Well, yeah, they have a list of all these things. The best high mass X-ray binaries.
Yeah.
Oh yeah, there's lists of all
No,
those
no,
things.
the list of like things that went into, like, into the said black.
Well, you don't know, you can't, the thing is, if you're far enough away and something is falling into the black hole, you wouldn't, because of the way speeds work and you're in a different reference frame,
Yeah.
you wouldn't see something fall in.
Oh.
It would take almost forever to see somebody fall in. Whereas if you were the person falling in, you'd fall in and you almost wouldn't notice anything. That's where the difference is coming. So no, we can't see things fall in. We do know that black holes are feeding, because if they're spewing jets out, there has to be material falling in. So we know material's falling in, but we're not physically seeing, okay? Like, oh, there's a pizza, falling in or something like that. Yeah, we can't do that. Yeah, we're not at that level. We just know, we do know if a black hole is feeding or not. That's the whole quasar phenomenon. Those are black holes, big black holes early in the history of a galaxy that are actively feeding, and that's why the middles of quasars are so bright. So a big black hole is fundamental to quasars.
Cool, thank you.
Do we have one last question for our
We do.
Dr.
What's the
Durrell?
other side of a black hole?
What's the other side of a black hole? That's a good question. I don't know what the other side of a black hole is. Probably extra parking. I don't know. I mean, the thing is, some of the light in those photon rings is from stuff on the other side of the black hole. And it's just, normally it would go that way. If this is the black hole, normally light would go that way, but there's so much gravity, some of that is coming around. So you're actually seeing some of the back in those pictures. That's the weird thing. That's how weird things get when you're close to a black hole. So in a sense, some of that light is from behind, and it's no different.
Thank you.
Yeah, something on the other side.
Yeah.
They'll be seeing us.
Yeah. Yeah, if they're looking for us. They probably have other things on their mind. Boy, it's hot in here. No. Thank you.
So you want to visit a black hole. You've packed your bags, you've updated your passport, and you're basically ready to jump on a spaceship and blast off. However, before you do that, I have just one piece of advice. Don't. Okay? If you really must go, I suppose you should at least know a few things about black holes before you leave. First, you should know exactly what a black hole is. A black hole is a physical object in space, just like everything else. It's made up of a tiny but massive point where gravity and density are infinite, a line beyond which everything, including light, can only fall into that tiny point, and sometimes some glowing stuff orbiting around it, and maybe some radiation. So basically, here is kinda bad, here is really bad, and here is safe. Also, black holes mostly come in two sizes. Don't ask me why, we still aren't sure. However, a black hole is also not a lot of things. It is not a hole, a cosmic vacuum cleaner, a portal to another dimension populated by unicorns and space potatoes, and absolutely not a good place to vacation. Okay, fine. I guess next you'll need to know how to find a black hole. Though technically black holes could just sneak up behind you, they likely won't. The nearest known one is 3,000 light years away anyway. However, if you were to go looking for one, there are a couple of good ways to find them. First, black holes tend to mess with their environment, so you can sometimes use interesting clues, such as a bunch of stuff orbiting what appears to be nothing. And second, as we mentioned before, there's often glowing stuff orbiting around them, caused by, well, when things get too close. So now that you've found a black hole and clearly aren't listening to me saying not to go, it's time for a few important safety considerations. First of all, the good news is that as long as you stay far away, black holes aren't all that bad. However, as you get closer, you need to keep a few things in mind. The radiation near the black hole can be extremely deadly. The chances of escape get slimmer the closer you get. And if you get close enough, you now have to worry about being stretched into a giant noodle and time getting really weird. So, unless you have great radiation shields, a faster-than-light spaceship, or you're completely indestructible, you should probably just stay away. Well, that pretty much sums up black holes, at least before things start getting really complicated. But before you go for real, please refer to the handy brochure in your spacesuit pocket, since there's quite a bit to remember. Now then, remember your tickets, enjoy your trip, and please, be careful.